people so they can hear you also.
They can check.
L-R.
No,
R. Okay, JR.
I'm gonna mute this because I can hear it. Can the people who are joining live confirm that they can hear me right now?
Okay, we are back for the first physics talk of the school. It is my great pleasure to introduce you to, or her to you, Cynthia Keppel, Associate Director for Experimental Physics at the lab, former professor at Hampton University, friend and colleague of mine, and also former boss of mine. I can hear in part because she persuaded me to, and I stayed. So it was good for me. Tia will give you an overview of what we are doing here. So please go ahead.
Even better for us. So this is really great to see all of you guys. I actually love the HUGS program. I was a HUGS student sometime way back and a former HUGS director. And so it's really, really great to be a HUGS speaker. So this is fun. So I will apologize to you guys a little bit in advance in that as I was working, I modified my talk. I gave the HUGS lecture last year as well, the opening one. And I wanted to change it and modify it and add some new things and change how it went. And it got fully corrupted like about an hour ago. And so I freaked out. So anyway, a couple of my slides don't have text. So you have to pay extra close attention because I'll have to talk through the pictures. But I got all the pictures back up anyway. So I made progress. So hopefully this works. And maybe I'll try to make a version anyway that has the text for the Indigo for you guys to have that. Right on that. But hopefully it's not too bad. And just ask questions because that's what you're here for anyway, right? So it'll be good. We'll get there. All right. So starting very big picture. Why doesn't that go away? Will it go away eventually? Zoom stuff at the top?
No.
No, we can get rid of this.
Just maybe look at the chat. Maybe it's angry at that.
Oh, I see. Ah, magic. Okay, cool. All right. That's just going to keep happening if we get things in the chat. But okay, we'll see how it goes. At any rate, I kind of go back and forth between very broad brush, kind of maybe too simple for some of you, big picture what we're doing, and then some more detail. Like at the end, we'll be zipping along at 100 miles an hour. It's okay if you don't pick all that up and it's way too much. So just to try to hit everybody, because I know y'all are at a bunch of different levels. So we'll give that a go. So let's start super basic. I love this picture. It's pretty. So it's National Geographic, and it's the birth and death of the universe going through time and all the different stages. And so where does JLab sit in this picture of trying to study these giant cosmic questions? We sit both here and here, the first and second steps. And so you don't need to read this little tiny print. But at the very, very beginning, in the first sub-nanosecond of all of the universe, there's a little bit smaller than a golf ball size thing of everything. So you need the table to build in the country, all the countries, the world, the universe, the sun, star, everything, right, is in this little golf ball. And this golf ball is full of quarks, kind of it, all right? And then quarks are a really strong repulsive force, right? And as this repulsive force takes over, this golf ball expands to eventually become the universe. But the first thing that it does is these quarks become protons and neutrons. And that's like in the first millisecond. So what we really want to look at Jefferson Lab are these two things: the fundamental structure of visible matter, so the quarks and gluons that make this up, but also the borderline of how these things form hadrons, mesons, nucleons, and nuclei, right? So not just the sort of structure so much of the quarks, but how matter is formed, that part. So that's where we sit, and that's our big overarching mission, that maybe all of our entire experimental program maybe sits under those questions broadly. So that's where we are in the very, very big picture. All right, why am I not switching? Okay, I'll switch over here. Oh, I tried to flip the slide. Yeah, it's because I did the thing. Yep. Okay. So how do we do that? You guys, I'm sure, probably have a picture for this, but I want to make a point that isn't always made. So typically we do the analogy of using Heisenberg uncertainty, or not even analogy, we deploy it and we say, okay, the distance that we want to probe is proportional to the wavelength of the probe that we're going to use, which is inversely proportional to the energy. And so that tells us that if I want to look at something super small, like a quark inside a nucleon, then I need to have something very high energy. So probably all of us as physicists have something like that picture. And we probably have another picture as well. We're thinking about, well, how do we see anything, right? How do I see this floor or this screen, right? My eyeball's not directly interacting with the floor or the screen, right? So, but photons are bouncing down from the light source, bouncing off of that, and bouncing into my eye. My eye is a super sensitive photon detector. It tells me things like the wavelength, which I translate as color, the amount of photons I translate as intensity, all that. So that's how we see anything. So what are we going to do for any of these kind of experiments, right? We're going to go to very high energies. We're going to get a probe that we can deploy at very high energies. We're going to make detector systems like giant eyeballs, and we're going to start counting them, right? Counting the probes to get intensity, and we're going to start walking around it to get a feeling for shape and size. But the point that's not often made in that whole picture, which I'm guessing you guys all have a feeling for, it's the giant microscope picture, is why electrons, right? Why are there proton machines and electron machines, right? Jefferson Lab is the electron accelerator facility for the world. Why would you use electrons if what you want to answer is that cosmic question of what is the structure of visible matter, right? So you don't need to create new matter. So you don't need to do a proton anti-proton collision like you're at CERN or something, because there you're trying to create new forms of matter and study that. We want to study ordinary matter. How do protons and neutrons form nuclei? So why do you use electrons? Here it is. It's because they use the electromagnetic force and they're point-like, right? So two properties that make electrons perfect for doing this kind of science. They're point-like, so they're not going to modify what they're probing very much. They don't have the size of the probe, and besides being very high energy, but they themselves are point-like. The other thing is that we understand the electromagnetic interaction. So we can use that to get at any interactions we don't understand, like the strong force physics that we're trying to get at. So hence, you build an electron machine if what you want to do is study ordinary matter, because you want to probe something that you can just put there as a target. So that's what we do. Sorry, let me go backwards one more time. So this is a picture I'm sure you guys as physicists have seen many times. The going down in size commensurate with going up in energy being the same thing. But this is kind of a static picture. We have an atom and we have protons and neutrons inside and we get down to the quarks, but that's a building block picture. And that building block picture is very, doesn't display the amazing dynamics that we have to take into account. So I just like to point out that these things are not static. They're really moving very quickly, right? So inside the nucleus, the protons and neutrons are moving roughly 3/4 the speed of light, right, in that tiny space. So they're zipping around, and they reside in a small space, but the quarks and gluons confined inside of any given proton or neutron are moving essentially the speed of light. So this is a very dynamic system. They're not building blocks at all. And in fact, it's this motion and energy that we're going to talk about that actually is the more important thing for understanding visible matter and the mass of things. So, okay, now here's my first slide where I lost all of my text. And it's terrible because there's so much meat to it. So now you guys have to pay intense attention to me because I don't have text. So now I'm gonna have to talk really slow. No, I'm kidding. We'll get there. Okay, so what I want to show you here is these two pictures. So I want to start with nucleons. And so we're gonna have quarks bound in the nucleus. Because remember in that very first slide, we had the two balls in the cosmic questions, right? The first one is that sub golf ball filled with quarks, right? So we're going to focus on the quarks initially. So this is the running coupling strong force coupling constant, which we call alpha S, not constant factor. So, and it changes. This is energy. So as we said just before, as the energy goes up, the distance scale goes down. Right. So this is the force between quarks. So it's a kind of a measure of the force between quarks. As I go out here, I'm going down in distance, right? And so the force is actually dropping to 0. So that's what we call asymptotic freedom. So remember this thing, right? As we're going closer and closer, the force is going to 0 because we're going to go quite against that in a moment. And when you think about it, it's sort of surprising. So think about that for a moment. That's asymptotic freedom. What does that mean? It means that the quarks are free asymptotically, right, as they go close together. But then when they start to get pulled apart, so that's back here at lower energies, the force gets infinite. And in fact, it gets so big that as you pull the quarks further and further apart, rather than nature letting us have a free quark, if you get enough force in there, instead, what happens is this picture, this is a drawing by David Gross, is that the quarks pull and pull and pull, that the gluons that are binding them, it's kind of like, I'll go to an analogy in a moment, but they basically pull up, they don't pull apart, they create new quarks that go and couple and pair with them and go on. So you get enough energy involved in that pulling them apart that energy creates more quarks. So you never get one quark out by itself. So at one level, we have this quarks are free. At this other level, they can never be alone. I don't know what happened there, but we'll worry about that in a minute. So these are the two kind of faces or manifestations of what we have for this nucleon structure. And yeah, so let me just leave it there. Hold those two in your mind while I talk about nuclei, because now we're going to have something really different. Here's nuclear force, because so now we're on that second circle in the cosmic questions. So here's the nuclear force. It's repulsive up here and attractive down here. And I apologize for that because we wanted attractive to be on the positive side, negative, positive, negative. But anyway, repulsive here and negative. So now, what do you have? This is the electrostatic Coulomb force. So think about protons and nucleus, protons positively charged, right? So you know, opposites attract, likes repel. So at some point, the protons, you think that they're in the nucleus, why isn't the nucleus just blowing apart? Because it's got these two positive protons, right? They should be repelling and repelling and repelling because there's nothing else in there with charge. Yeah, but they don't do that. But that's what you would have from the electrostatic Coulomb force, right? That would be just, that's what we know. That's electromagnetism, opposites attract, likes repel. But instead, we have this strong nuclear force as well, which does this thing. So this is a weird force. So as these things get closer and closer, it actually becomes infinitely repulsive there, yeah? And then they get further apart and it becomes quite strongly attractive. So these nucleons have a repulsive nature as they get further apart, an attractive nature as they get close, and then the force goes to 0 again as they get further, and the force goes back to 0 again as they get further. And in fact, eventually the Coulomb force takes over, and that's kind of the world that we're used to living in on a more macroscopic scale. All right, now think about everything. Now what I want to tell you is something that's puzzling, and a part of why Jefferson Lab exists, right? Is that both of these things, this one and this one, are all the strong nuclear force. But wait a minute, what did I tell you? I said, when these quarks are super close together, they're free. And as you pull them apart, they're infinitely strong force binding them back together. And what did we just say about the nuclei, right? When the nuclei are close to each other, there's this near infinite repulsive force. Then there's an area where they're attractive, but then when they're farther apart, the force is zero. So how can that be the same force, right? It's exactly opposite in manifestation, but it's the same force going on, yeah? So except for this kind of dipping thing, but okay. Other than that, it's the same force. So that's quite strange what's happening there. And yet these are both the strong force, right? So strong nuclear force, strong force, binds quarks, binds protons, binds neutrons, all of these things are happening due to that. So what do we think is really happening is something like this, is you have within any given neutron or proton, these quarks are bound together and they're obeying the rules of asymptotic freedom. And as they get further away, they're infinitely bound or enough to create what? Create new quarks. And so the new quarks get created in those pairs because you can never have one by itself. And you get these mesons. And now what's happening is that same force that created those, these mesons are actually mediating the force between the protons and neutrons. And that's how you get the same force that's giving you two drastically different manifestations, right? So this is how we picture both the quarks bound in the nucleon, the nuclei bound together, how those things are interacting, all from kind of one picture. That's our current thinking. I'm going to guarantee that something I told you in there is somehow wrong, okay? Because you're going to figure it out 10 years from now. Because we don't actually know how all of that works really well. We don't know a bunch of things, like we don't know why we can't have, why we don't have 5 quarks, like one of these guys living with one of these, or we kind of do, but only for a little bit, or why don't we have glue balls and things like that. There's a whole bunch of things we don't understand, which our current thinking would allow, but this is the picture that we have right now. And this is what the kind of thing that Jefferson Lab's job is to elucidate, say how big these forces are, how large these radii are, what kinds of new structures we can make out of these, all of that. In the big picture, that's what we're trying to do. Yeah.
Sorry, could you elaborate the contrasting manifestations?
Sure. Yes, yes, yes. So here we go. So this is 2 quarks or 3 quarks, right? This is a couple quarks, yeah? And so these guys, when they get close together, there's essentially no force. They're free, right? And then they start to go apart. And they get infinite force pushing them back together. Yeah, that's 2 quarks in the nucleon. Then in the nucleus, what happens? In the nucleus, you have 2 forces because you also have the Coulomb force coming in. It's there between the quarks, but it's tiny. So in the nucleus, just look at the strong nuclear force part here. Completely different. As these guys get close together, they don't get free, right? They in fact experience a near infinite repulsion. And then as they get far away, unlike the incredibly strong pull back, they get 0 force. And then in between, on top of all that, in between, there's an attraction that isn't even, that it's not there in the other picture. So they're vastly different manifestations of exactly the same underlying phenomenon, we think. Okay. So far, yeah, so very, very strong and hard to really get exactly from one to the other. And this is the picture that we have right now of how to move about from one to the other. But again, I don't know what it is. I wish I did, but I told you something wrong. Okay. So well, you guys will tell us. All right, so how do we know all this? And what we do know is that we've had success. We've been using leptons are, of course, electrons, but also neutrinos and muons. A powerful tool for studying nuclear structure for all the reasons I told you before. It's point-like, it uses electromagnetic interaction. We've been doing this for decades now. Not here at Jefferson Lab for decades. We as a nuclear physics community have. So it's a clean probe. We can vary the wavelength in a controlled way. You only get the electromagnetic interaction, so that's helpful. But there are challenges. The interactions are weak, which means you tend to have very small cross sections. Not weak like weak nuclear force, just not strong. They are small. This means that you have to have a large intensity machine. You'd also like to do coincidence measurements to see what else comes out besides just the scattered electron. Because you'd like to do all that, and because there's lots we still don't know, we have Jefferson Lab. So this is a kind of overview. This single program was true until about a year ago. We're actually now allowed to expand out. So that's kind of exciting. You'll hear some about advanced computing, I think, and other things as you're around for these few weeks. But we have been in operation since '95. We use the Continuous Electron Beam Accelerator facility. That's what we call our accelerator. So it's CBAF at Jefferson Lab. And it runs around below the ground, this kind of structure here. There's two linear accelerators, one over here and one over here. And so rather than go many miles around, we actually have a racetrack structure where the electrons are accelerated in a linear accelerator, brought around, accelerated again, brought around, accelerated again, brought around like that 5.5 times. So it sits on top of itself rather than being as large as if you were to spread that out. Our mission, as I said, is we want to understand the structure of matter through fundamental research, and then also to advance accelerator nuclear science technology. And I'll say one slide about that near the end, if I have time. So we have the largest nuclear physics community in the world, and it's still growing. We have about 700 employees, including 27 joint faculty, or joint and bridge faculty. These are people who have positions at universities as well. We have about 170-acre site, about 1,700 active users. These users actually come from 39 countries and 278 institutions. So it's a broad worldwide physics community. And we also work with K through 12 programs, so younger students and teachers, and grant about 1/3 of the US PhDs nationally come from here. US PhDs in nuclear physics come from Jefferson Lab, come from an experiment or theory work done at Jefferson Lab. So broad brush, that's our site. That's what we're doing. Here's the same picture. I'm trying to give you a better feeling what I was saying about a linear accelerator around, accelerator around, accelerator around, like that. All this stuff is under the ground. And then the beam can go, so initially it is injected. So we have an injector, where we get the electrons from, and I guess you'll get an accelerator talk, so you'll hear about this, but more or less you kind of bubble them off of anything, right? Because there's electrons in anything. And so if you can put a high voltage to a conductor, electrons will become close to free and you can pull them off and move them on. It's not all that simple, and our injector people are really, really good, and they do a lot of amazing things to polarize the beam and things like that. But there's an injector. This is the first source of the electrons. Then they go through these linear accelerator regions. Through the world's largest helium refrigerator, because we're a fully superconducting accelerator facility, and so a lot of cryogenic engineering going on. And then we recirculate, as I said, recirculate the beam. So as you can imagine, the electron beam coming through on first pass has a very different energy from the electron beam coming in on fifth pass. So these magnets need to be different for each of those passes. So each of these layers is a kind of a different, it is definitely a different magnetic path, and it's associated with a particular energy. And then there's 4 experimental halls, 1, 2, 3, 4, where we actually, this is where the user community mostly works, is in designing and running the experiments that exist in the halls. And so this is just a better photo of what's inside the halls. I'll talk a little bit more about the physics contrast. What I can say is, although this kind of gives a feeling what is the main physics program in each of the halls, what I would say is that each hall has somewhat different equipment, and we need to do that. So you'd say, why do you have 4 halls? Why do you have guns and see like that? And actually they're different. So you can imagine an experiment where what you want to see is really carefully electron in, electron out, and map that out with the highest precision you possibly can. right? In that case, you really want to control, for instance, the focusing, the optics, the magnetic fields, everything involved in making sure you understand the incoming and outgoing electron. Was it an electron? Was it something else? What exactly was its energy? All those things, and trying to focus in on that. That's what's kind of done in halls A and C. And another kind of experiment, maybe what you want to do is look at everything that comes out. So now you're going to have to sacrifice precision, right? Because you're trying to look at everything. So you can't be all things to all people, right? And so if you want to know if that was an electron or a pion, or if that was a pion or a kaon, or if that was a proton or a pion, then all those kind of particle ID detectors means that you're not focusing in on just that electron to get it perfectly, right? So you build a big onion and you put your detector in the center of the onion, and each layer of the onion is a different detector. And that's what's kind of done in Hall B and Hall D, except Hall D is particularly tuned to have a photon beam coming in. And then the difference between A and C is that Hall A actually has multiple experiments that we put on and take off the floor. So we put new equipment in. So we have to do all of those things. So you need 4 experimental halls. Or 6, no, you need 4 at least, to do all the science we want to do. Also to serve this large user community. So these are particle detectors. Broad brush, any one of these things weighs about 1,000 tons. So that's more or less the same as about like 5 747s or something like that. So they're very large pieces of equipment. But basically they're particle detectors. And I like to use this analogy, like you're looking at a water wave. And if you look at a water wave and you look at the height of the wave and the width of the wave and how fast they're going away and how fast they're going on, it gives you information about the ship that created them, right? This aircraft carrier, you're in Hampton Roads, so aircraft carriers are around here, will give a big old wake, right? That's going to go on, and you don't want to get your little boat caught in the wake behind it, right? And oh, that was a big boat that went by, right? Whereas this guy's not going to be in the hard part of it, yeah? So at any rate, we look at the paths of the particles. We don't typically trap the particles. They go on out into the shielding, which is why all those experimental halls were under the ground, right? Just like the accelerator here. All right, so PAC approved experiments. We generally put them in broad brush into these 6 topics here. And then here's our 4 halls, and this is the number of experiments in each hall. And so we've completed now about 32 experiments. This, I should say, is in the what we call the 12 JET era. About 5-6 years ago, our laboratory doubled our energy to go to 12 GeV as for the electron energy. And so people came and proposed experiments for 12 GeV. So we've completed about 32.2 of them, and we have about 52.3 remaining. And our program advisory committee that gives a science rating and approves or disapproves experiments that are proposed for the laboratory meets annually. So this number, it's not like we're going to go click, 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 and get rid of that and then we're done, right? Because our user community is brilliant and they keep thinking of new things to do, new questions to answer. But this is where we are at the moment to give you a feeling for that. And if you look over here, you'll see things like, as I was saying, we don't, questions that we still have, the 3-dimensional structure of hadrons. So not only, again, not just a building block picture like there's 3 quarks and a proton or something, because there's more than 3 quarks, but also, and they're moving really fast, but can you get a picture of their 3-dimensional structure? Like, how are they moving? Where are they moving? Are they moving around the outside, inside? What's going on, right? Do they cause changes in the proton structure as it's dynamically moving? All those things sits in the 3D structure. That's very different from hadrons and cold nuclear matter, which is more about how do these protons and neutrons make up nuclei. Right, and so there's we divide them that way, and you'll see that pretty much we're evenly split amongst all these questions. So what I thought I would do for most of my talk, there's not a thing in here, so a clock thing.
There used to be.
There used to be. I know, that's why I keep doing this. So you're wondering, like, we're all doing that. There was a clock here.
So
You're good. So
you're at the half-hour mark.
good. Okay, that's probably perfect. So what I'm going to do is do 2 things. I'm going to show you a couple experiments that are running in a little more detail, and then we're just going to zip through a smattering of other ones, so you just get a kind of a feeling and see some things, and it'll give you a feeling for the magnitude of the effort, I hope, because there is not time to talk about the science of Jefferson Lab, because there's 52 experiments, right? And I could talk for an hour at least on each one of those experiments, and you guys would be really sick of me. So we're not going to do that. So I picked 2 ones that are running right now to give you a feeling for those experiments and how they link together. And and then I'll kind of whoosh through the program that's running at the moment. So this is nice because I chose this one in part because it's running and in part because it hits those two circles in the big cosmic questions and the thing I told you about linking how quantum chromodynamics is going to link both nucleon and nuclear structure a bit. So in Hall A, we're running an experiment to look for the neutron form factor. So if you think about the neutron form factor, a form factor tells you what? It tells you the charge distribution. Yeah. And so you can tell me, well, neutrons are neutral. They probably don't have a charge distribution, right? That seems weird, but the answer is that they do have a charge distribution. And so it looks something like this, where this is the radius. And remember from those pictures before about the size of distance between nucleons, the size of the nucleon, right? You're going to look for that sort of equilibrium position amongst all the forces that go on. So at its radius, we're neutral. But it does have this interesting positive negative structure to it. And these are experiments that have been measuring this form factor and they come up with this positive negative structure. And what is that? That is actually the fact that sometimes the neutron becomes a proton and a pi minus. And this is the picture, whereas proton's positive and pi minus is negative. Yes, we have a positive negative structure. And so it can fluctuate. That neutron can become a proton pi minus, go back to being a neutron. And it can do that. And because of why? Because those quarks are dynamic, right? And so that's the picture that we had where you're maybe exchanging the pions is the force that bonds and causes the interactions between the protons and the neutrons that binds and makes up nuclei. So even a single neutron will do this, of course, if all of them do it. So this is the picture. So we would like to understand this better, measure it out to further momenta, muck around with what is the real number in here, things like that. So we want to measure the neutron form factor, very, very basic measurement for the neutron structure. So this is part of something called the Super Big Bite Spectrometer program in Hall A. So this is another aerial view of the lab. There are those two LINACs, and here are halls A, B, and C. And Hall A is pictured here. And this is nice. This is what I was hoping would give you a feeling for the magnitude of these experiments. This was before last year. There were two large focusing spectrometers in the hall. There's a person over here to give you a feeling for the size. And one of these is fully kind of parked, removed, pushed to the side, gone off the floor. And the other one is kind of pulled over. And all of this equipment, this was actually mid-installation, but this is called the Super Big Bite Spectrometer system. So it has two magnets, large detector systems that actually also fill in the gap between here, a second detector system here, a bunch of electronics, and a beam pipe, all of these things. And so the staff and experimental scientists and user community people here do things like this, right? We take down an entire large experiment, put another entire large experiment up in order to look at these measurements. And this is happening over the course of maybe 9 or 10 months, trying to do all this work. So engineers, technical staff, all of these people working together. These are large efforts to do these experiments. So this is a particularly large effort, but it is not the largest that we've done at all. So in this Super Big Bite program, this is called the Super Big Bite Spectrometer. That's because it has a large opening here, relatively speaking, is dedicated to precision measurements of these form factors. And the other thing that we will do, so to get at the neutron form factor, we used a polarized helium-3 target, which we used in Hall C actually in 2020. So this is, like I said, we're doing these big efforts, moving things around. It turns out that helium-3, the gas, you can polarize. How would you polarize it? So first of all, you have a filled helium-3 cell. So if you follow me, there's a little glass cell going here. And we put this glass cell in the path of the beam. And then we can polarize this helium-3 by letting it go up here, and we run many lasers, a lot of laser power into the helium, and we heat it up so that it diffuses down and goes through here. And so we have polarized helium-3. It turns out that the part of the helium-3, the proton and neutron, cancel each other out in the polarization, created an essentially a polarized neutron target for yourself. So we want to measure the neutron form factor, particular charge form factor. So having polarized neutron target is a good thing to use. Right now, you can use your electron beam to scatter off of the neutron and look at where the electron beam goes based on the charge it encounters, but also it's polarized, right? So the angular dependence is going to give you information about the charge distribution. So this thing we used in Hall C, and now we've upgraded it to make it even bigger and better and handle more laser power. And we've moved it over into, oh no, and we've moved it over into Hall A. So not only are we installing and building new equipment, we're also repurposing and upgrading old equipment. All of that to measure these form factors. And this is terrible. So I am very sorry. But I can walk you through this, but don't look sideways because it's not even got the whole things. Remember how I said my talk got disrupted? So this is another manifestation of that. But anyway, what I would have shown you is that we have, you have an electric and a magnetic form factor. So the charge distribution essentially and the magnetic distribution, so picking up the motion for the proton and the neutron. So that's 4 form factors you want to get. And so the SBS program will measure all 4 of them with the highest precision and to highest momentum transfer. So again, the smallest distance that's ever been done before. So that's what that experiment is aiming at doing. We did one of them, GMP already, and we're working on GEN now. Then we'll move to GEP and GMN. So we're moving along the form factors in this SBS program. And then we're going to switch to beyond the standard model search. So we go all over the place in the halls, but that's what we're doing right now. Sorry that this isn't showing up, but what this would have showed you is just the reach and the reach kinematically. What is the momentum of this experiment, the reach and the precision. Okay. Which is relevant, what's going on in Hall C. So this is kind of nice. This is another way to use that. So if you think about the neutron sometimes being a proton and a pion, you can also think that the proton itself is also sometimes going to be a nucleon and a pion. And this is, you can prove this to yourself, but also leverage it. So suppose that you have that nucleon and that pion, and you bring the electron beam in, and you get the pion and the scattered electron, you measure them both. Right? And now you think about like a pool ball type experiment where you know the incoming electron energy really, really well. And now you measure the energy and momentum of the electron and the pion going out with particle ID to be sure you have an electron and pion, and you reconstruct exactly the energy here, right? So you have an elastic scattering event, right? This convinces you that you hit that pion that was in there, right? You got a pion, and now you can use that as a kind of a pion target. And so we can measure the pion form factor as well. And it turns out that you want to do something called longitudinal transverse separation in order to actually get at the pion form factors, because what we want is part of this component. So the pion is exciting. It's a QCD laboratory because it is the simplest bound system. It's 2 quarks bound together. So if we can't describe 2 quarks, well, that's simplest, right? So hopefully we can, but anyway, going to 3 and 6 and 100 or something for nuclei is going to be harder. So we'd like to understand the pion well. However, there are no free pion targets in nature. So we have to do experiments like this where we get at a pion inside a nucleus, inside a nucleon is the only way that we can do that. So they're harder experimentally, albeit perhaps easier theoretically to describe. So it can be calculated exactly at very high momentum transfers. But what we do is, I said, we indirectly measure the pion form factor using the pion cloud of the proton. So this means that we have a proton target, electron coming in, electron going out, and we measure the pi plus neutron. The same way a neutron can be a proton pi minus, the proton can be a pi plus neutron. And so here's what the online results look like, for instance. So this is a clean separation of the neutron and the pion state. So you can actually see it in the missing mass that we're getting both of these things. So that's a further conviction that this is the right picture. This is just to show you that we're doing it in Hall C. This is a photo of Hall C and going out to high momentum and high precision. And we will also do this for the kaons. So periodically there's a kaon in the nucleon as well. And that's fascinating because the kaon has a strange force. Right, a strange quark, sorry, it has a strange quark in it. And so that means that some part of the time as that proton or neutron are fluctuating into a nucleon and a meson, sometimes there's strange quarks involved in that. So they're heavier. So you want to think of the proton as being, say, a UUG, right? but it's not only an UUD, right? It's a very dynamic system. It's a UUD plus an S and an S bar and some other bunch of stuff. And so sometimes you can actually get that kaon that's created from that SS bar. This is a very important measurement. Another way, just to give you, again, a feeling for what's going on, we have this picture, very static picture of the elementary particles and elementary forces. And if you think about the nucleon, we could say that the proton, for instance, is an up, up, down, but that would actually give you that the proton should weigh about 10 MeV. So this should be another clue that our static picture is not a good one. And also the proton spin, when we measure the spin, only about a quarter of it is carried by those up, up, down quarks. There's something else going on. The proton mass is closer to a GeV, 938 MeV or so. And it actually is coming from all of that dynamic motion, all of those pions and other things that are inside of there are generating all of that. And in fact, generating, therefore, remember, most of the mass of the known universe. So it's not like a Higgs mechanism for particle physicists in here, right? More than 90% of the mass is actually sitting in quantum thermodynamics from these dynamic interactions. This is actually from a talk that Craig Roberts gave, and I don't want to go into all of it, except it's flashy, but to say that now that we can make sort of practical, this is from a theorist, right? So difficult experimental pion and kaon targets, we can move beyond the proton to explore and explain an entirely different form of hadronic matter, the mesons, with which the universe would not exist because the mesons are going to be the component of that nuclear force. So from a nucleon picture, or from a quark picture, they're the simplest. There's two of them make up a meson. From a nuclear picture, they're carrying a nuclear force. And so what we want to get at is the balance between those things and understand both. It's nice that we can study pions. But that is just one component of the Jefferson Lab program. So I thought I would show you that because we're in, actually, when you go out to the halls, when you guys get a tour, that's what you're going to see being set up in halls A and C are those two experiments right now. But there's two other halls and there's other experiments proposed for A and C, looking at different things and related things. So this is a feeling, this is a look at the recent life of a hall. This is hall D. This is experiments and runs up to 23. And again, this means in this 12 GeV era. So not since the beginning of Jefferson Lab, just in our recent era. So since 17. So multiple publications. Hall D is tagged photon beam. We actually send the electron beam through a diamond radiator, and that gives us polarized photons at about 9 GeV. And that's what this hall is designed to do, is to look at particles created by interactions with those polarized photons. It's a hermetic spectrometer. That means it's an onion. Okay. So it's a they're getting full acceptance. So all of the particles that come out of the interaction. And lots of statistics of photo production. So this is the experiments that are proposed for Hall D, the program advisory committee, or PAC approved days, and percentage of where we are with how we're running this on. And so you see different things. You know, each of these are different experiments. Sometimes a very different experimental collaboration coming in, changeover within the hall, and we're clicking through and more things come in and putting those in the queue and moving along. So that's Hall D. Here's some recent results and data analysis in progress. Also, to give you a feeling for the breadth of the program, this is an axion search. Axions are a kind of a dark matter candidate. So looking for axions. So this is actually gamma P goes to, and you can see over here what they're looking for in the interaction. This would indicate that there was an exchange of an axion. That's what's happening. So axion searches to looking at these asymmetries over here. This is what Hall D was proposed for. What we're trying to do is look for things with, in particular, the difference between natural and unnatural parities. What we're looking for are exotic mesons. So we want things that are in principle allowed by QCD, but which we don't see. So what we see typically, right, are the UD or UDD, the protons and neutrons, or we see these mesons like pions. So if they're either two quarks, or well, a quark and a quark pair of some kind, or they're three quarks. But you could have five, right? You have these things combined, which we know happens virtually, like those experiments in A and C I told you about. But why don't you have like bound objects that just exist like that? Right, and so why not is a big question. So that's in part what this call is looking for, are these hybrid mesons. And glue balls, objects simply composed of gluons or largely composed of gluons. Either one would be good. So they're going at that. Here's some other physics that they can do because they're tuned to look for produced particles, specific particles. Remember, it's that big hermetic detector. They can, for instance, look for the J psi. So this is the photon coming into the proton going out, and the J psi. So the J psi, just like I told you when we produce kaons, that's kind of exciting because that means it's a strange quark, right? The J psi comes from the charm quark. So this is actually even a step further in looking at what happens in this interaction inside the nucleons, creating these new particles as part of ordinary matter. So this is J psi. They're going to continue to do that, building new detectors for calorimeter, transition radiation detectors, up our game in doing this to higher precision. And then something completely different, right? So you've seen exotic mesons, you've seen axion searches, you've seen J psi production, and this is looking at more conventional nuclear physics. This is looking for short range correlations for the first time using a photon beam. And here, what we're looking at is nuclei, so big nuclei, right? Carbon, something like that, not nucleons, nuclei. And as we said, it's very dynamic. These nucleons are moving around 3/4 speed of light, something like that. And so at some point they're going very, very high momentum. Yeah. And those very high momenta come from what we call short range correlations. So that's when the nucleons in the nuclei are very close to each other. So they're interacting very strongly. They're moving very fast. And so we want to look at that and map that out. So they're doing that. So nuclear physics. So I like this because it's giving you all these different questions, different kinds of things that we can use by changing this equipment somewhat, right? Not a small effort, but it's kind of a vast amount of questions our user community can ask that we can handle in these halls. Yes. No kinematic fit. So yeah, so what they're doing here for the short range correlation studies, I also have added in something called color transparency, which I didn't talk about, but that's what it's speaking to. The color transparency is basically when a nucleon gets hit with the electron beam with very, very high momentum transfer. So it's got a lot of momentum transfer to it. Typical thing is it breaks apart. That's deep inelastic scattering, right? Just breaks apart. Sometimes not. Sometimes it holds together. And sometimes it not only holds together, but it makes its way out of the nucleus. So in order to both hold together and make its way out of the nucleus, it has to be in a very, very teeny configuration, which is very, very tightly bound, so it doesn't interact with all the other nucleons that makes it out. So that's called color transparency because the nucleus is transparent to it. So this has been observed in mesons and not in nucleons. So that's what they're trying to do. But the problem is you don't know what the basis is for that. Right, so if you don't fully know the momentum distribution, right, so therefore sort of the sizing of the nucleons, you could try to fit for that and compare it to something, but then you're comparing it to something you don't know exactly, right? So it's trying to get a baseline. Is that helpful? Okay. All right. So I only have 5 minutes, so I'm going to zip through a little bit more to just say that not only that, but Hall D, for example, is preparing for the next round of experiments. So we're going to continue to look for these hybrid mesons, and we need more detectors. So at the same time we're running these experiments and analyzing these experiments, we're also building detectors for the next group of experiments. So there's always a lot going on. And Hall C, I could do the same thing, but now I just talked about color transparency. So this is a color transparency experiment and a large momentum tail experiment as well. And then looking for something called the EMC effect, which I don't have time to talk about, and building more detectors, just like Hall D. So again, I just want to give you a feeling for the breadth of the program. Same thing in Hall B, but here they are really focused on looking at that three-dimensional structure that I touched on very early on when I showed the pack chart, where we don't want to just look at the static picture, but we actually want to understand at the same time both the charge and magnetic composition, but also the three-dimensional nature of that, so the momenta and the position. And both the transverse and longitudinal momenta, so a full picture of the nucleon. So that's going to take a lot of mapping out, and there's a broad program in Hall B designed to do that. They're also looking for heavy photons, which is a dark matter candidate search. So that's going on as well. Very neat equipment that sits right up just 2 millimeters from the beam, very tricky experimentally. And then also looking at nuclear effects. So looking for nuclei, doing things like those short range correlation studies. So again, the breadth of the program. Hall A is also doing parity violation experiments, which let you, for instance, measure the neutron radius, so not the charge radius, but the neutral radius of lead. This turns out to have a large impact on neutron stars and neutron star predictions. So this is actually one of our most cited papers from the era before 12 JeV, which was the 6 JeV, half the energy era, actually came from the astrophysics community, quoting the first neutron radius experiments from Jefferson Lab. And doing the same thing for calcium, it turns out that we did both of these experiments now, and everybody thought that we had this kind of locked down from a theory standpoint, kind of understanding why what predictions for the neutron radius for lead, and then you could use those theories and predict for calcium, and it turns out that they're not that. So we have a bit of a mystery going on there, but that's very new results. And then the last thing I wanted to say, and then I'll wind up, is that Jefferson Lab, I've talked a lot about the core science, the structure of hadrons, but there's a lot of other things going on. We look at, we look for fundamental forces. We also, as I said, have bearing on nuclear astrophysics, some theory and computation, which hopefully you'll hear about lattice calculations and things like that. Accelerator science and technology, cryogenics. I told you, world's largest helium refrigerator. We've got lots of cryo engineers here. All of these things, and then other applications of all this technology. So one of my personal favorite side hobbies is medical instrumentation. This is just an example of what you can do with, for instance, the very basic workhorses of nuclear science, scintillators and photomultiplier tubes. This is a device that moved out, the technology moved out from Jefferson Lab to do this. This is a comparison of a mammogram, which is a breast x-ray. So basically it's leveraging the fact that tumors are a little denser than healthier tissue. So x-ray can do just like a dental x-ray, right? X-ray beam detector goes through and your teeth cast a shadow because they're denser. So the tumors will cast a shadow because they're denser, but that's a structural picture and may not have all the information because the tumor is not much denser, right? Which is the case in this patient. There's not really a large density region. Another approach is what's called functional imaging, where there are certain substances which are preferentially taken up by tumors. In this case, it's a substance called sestamibi, which works with the mitochondria of tumors. But at any rate, it's a different substance preferentially taken up by tumors. If you can also do the nuclear chemistry to put a radioactive label on that, then it's going to what? It's going to go to the tumor and it's going to sit there and emit radioactivity, which we can now detect and take an image. So that's a functional image, right? You're taking a picture of where is most of the sesame taken up. So that's what this is. And so it's very clear here where the tumor is. In fact, it's not where you would have guessed in this, as it turns out. So this device, this detector sits here, and we've moved on. We actually licensed this patented license this technology to a company, which was bought by a larger company, which was bought by a larger company. But meanwhile, so this is out there. They've sold many, many units out there for patient imaging, but we thought we could use the same technology in the operating room where if you've removed, the physician has removed the tumor, put a detector over it to see if all the microscopic disease is gone that the surgeons can't see, try to detect it functionally. And then that was going well, but then they don't want this. So work on making wireless, and then they don't want to do this and look up at a computer screen, right? Because your patient's still sitting there in surgery. So we're trying to get imaging sitting on the, what we call the hockey puck, where it's the detector that sits there. So this is an example. There's multiple projects like this. So there's more, right? a decade of 12 GeV experiments still ahead of us. We might be getting a positron beam as well as an electron beam. So positrons have all of the benefits that I just told you that an electron beam does, because it's just the antimatter partner of the electron. However, we'll get different, for instance, parity experiments, which are different manifestations. So it's another handle that we can use to understand nuclear structure. And we might upgrade our energy again. We went from 6 to 12, and we're looking at going maybe to 22. More new detectors, plus the electron ion collider, which I'm sure you're going to hear a lot about, is coming, and we're in charge of a part of the accelerator and the detector region are being built and designed here at JLab. So I'm done. And I apologize for all the exciting experiments, which maybe some of you are students on, which I didn't get to talk about a lot, but Keppel@jlab.org, I'm pretty easy to find. Or actually, I'm not used to find some neat, but you can find. All right, thanks.
Now we are open for questions now. Please go ahead.
So the fire factor, since the fire is not is consistent, so it's not free, does it change the form factor compared to fire?
So that is, yeah, sure. So the question, it's a very good question, is if, because we're using these effective pion targets where the pion is part of a nucleon, is that the same as if we did have a free pion to study? So so the question is, hopefully, but we can check for it. And so the way that we can do that is to try to get as close to on shell as possible, right? So we want that real on shell pion. These are far off shell, right? They're virtual pions. So what we can do is look at the momentum dependence, the pion momentum dependence, right? And try to track that back to where it would be as close to zero, as low momentum as we can, right? And look at, do we have a significant change in that structure that we measure as we approach as close to the on shell as we can get experimentally. So that's what we do. So it's still an assumption that there's not some drastic change or something like that going right to on shell. We don't know that. We don't have a way, but we will, because there's actually an experiment coming on at CERN where they use pion beams. So they can measure, they don't have an electron, so we don't have an electron beam pion beam. That would be the ultimate experiment to do this. We don't have that, but they do have pion beams going through things. And so by bootstrapping between the real pion beams, the way that they measure the form factor and the way that we do, we think that we'll be able, as a broad nuclear physics community, we'll be able to get at that. But for our standpoint, what we do is we try to check the momentum dependence going back to the on shell. Helpful? It's a really good question. It's difficult. Yep. And we rely on our theorists to tell us that maybe we're close to on shell.
So kind of going off of that, I think when you had, is it kind of the similar reasoning for how they did the polarized neutron scattering? Because you're saying that it was the I forgot if it was like the spins of the protons that it
The cancel, that's right.
Canceled
That's
out
right.
with each other, because I know like I've seen stuff where they've done like, deuteron scattering, where they, scatter off the proton and the neutron simultaneously. So is this like elastic scattering where it's kind of like scattering off of the helium nucleus as a whole, or is this kind of getting it more to like a semi like deep and elastic where it's like going just off the neutron?
Yeah, so the way in actually the pion form factor and the neutron form factor, doing these elastic experiments is very helpful, because kinematically we actually get the neutron going out. And we know the incoming energy very well because we measure it. So we know the full energy. That's why I kind of liken it to a freshman physics like pool ball type any kind of scattering basic experiment, because all the total energy coming in, and the angles and energies going out, and that you only had those particles because you're detecting for everything. So you reconstruct the energy going back. So we call that elastic scattering. So we actually don't get the full thing because this neutron was sitting in its helium-3, right? So it's almost the same answer I'm going to give you is we're going to detect that neutron, and we're going to do this at various angles and momenta, right? And double check that it's not changing as we go lower and lower, basically, yeah. While of course changing the incoming electron beam momentum. So we have to do that because, and again, we have to rely on theory. We rely on the nuclear models of helium to tell us that this should be the case. In this case, it's expected that the polarized neutron approximates, the polarized neutron in helium-3 approximates a polarized neutron target. Not as well as we're assuming for the pion, actually. In this case, we're assuming we can get there to within like 6 or 7%. So they do have a big uncertainty on them. So we'd love to have a real polarized neutron target. And you could make them because there are neutrons in nature. The problem comes back to one of those other slides I showed you, that these are small cross sections. So we also, maybe we can measure for a year, but we can't measure for 20 years. So we also need to have a lot of whatever target we put in place and a very high intensity electron beam. So there's kind of the practicalities of experimental life come in. Sure.
There is one for the back.
How long do you typically run like a single experiment for, and how much data do you get?
Yeah, so we run, this is, there's a big range. I think the shortest experiment that we've run is on the order of days, maybe 2 or 3. That's very unusual. I can think of actually only 2 in the course of 6 jug to 12 jug, but it happens. Long ones go on for years. So something like the experiment that I told you would go next in Hall A, the parity experiment that we'll do next, that's probably going to run for about 3 years.
And that's just like continuous?
24 hours a day. We run about 30 weeks out of the year, 24 hours a day. The rest of the time is down for switching over the experimental halls as well as for maintenance and upgrades to the accelerator. So we have a kind of a natural, you guys will be here probably when we start up near the end of your school, and then we'll start up and we'll keep running up until a winter break in December, and then we'll go again for maybe January and February for a bit, and then we'll shut down again into June. That's kind of our cycle.
Yes, this is more like a general question. So you talked about search of pentaquarks, okay? And Alice recently established that pentaquark exists in the charm sector, but not in the straight sector, using a specific confined set of quarks. So now when different experiments have almost overlapping motivations, like what is your take on how these experiments should collaborate with each other, as collaboration across experiments?
So I actually, one of the things is, I believe, not just my take, but the physics community, if you find something super exciting like a pentaquark, right, well, you better go measure it, because he could have done in every best interest and attempt and everything, still something you didn't see that's something, right? But, you know, that can happen. And so actually, LHC pentaquark is still under scrutiny. But not scrutiny from a bad way, right? It's not anything bad. Like these are very hard experiments, not just at Jefferson Lab, but CERN everywhere. And so double checking is one of the things that this community does, especially for really hard stuff. So first of all, I think that is the spirit of cooperation, right? It's like, oh my gosh, that's very cool. We'll go try and see if we see it too, right? And we'll change quickly to try to do that too. So another thing about those program advisory committees, it's not in line like a train, like you propose first, you propose second, you propose third. So it's the order you're running in. No, we actually do it. Yeah, no, it can have scientific priority. So our searches for the pentaquark actually got pushed into line closer in order to hopefully help the community to look at what do we see. And then sometimes you can see something different about it than what they saw or something like that. So we begin to launch a new study. And then sometimes we just change order because it's experimentally expedient, right? Like this guy can run really well with this thing, this other hall, so we can do all the science together or something like that. So our scheduling is quite a complicated piece. So yeah, my personal take on how to go across the communities is to do as much interaction as you can. Theory, experiment, different experiments, different theories, work worldwide, because these are precious facilities. There's not many of them, there's a handful. And it's a huge effort to get any amount of this data out. And so sharing and discussing will help all of us do best. So many conferences and workshops, you know, and to try to talk to. Also, it's really hard to understand this stuff, right? So you need as much help as you can get to try to do that.
And this is also a special thing about JLab. So you can design experiments to answer a specific question comes up today. You design an experiment, you get it running, and so forth. So you can do these things much more difficult at LHC.
Yeah.
Bigger collaboration, you have that machine there. So here we have this flexibility. It's a very complementary and very different kind of collaboration and environment that you work in compared to LHC or RIC. So it's a very special thing that we have here at Jefferson Lab. And oftentimes there are still human scale experiments. So where other students have a chance of doing next to everything. Yeah. So it's still special in today's things. There was one question there and another there. So
thank you. Thinking farther into the future, how do you think the focus of research here might change as the EIC starts to complement the research being done here?
Yeah, so the EIC, of course, is much higher energy. It is a tribute to electron scattering, right? That this is way, but it's always going to be much higher energy and much lower luminosity. And that's just the nature of the machine. And so we're going to sit in this lower energy, higher luminosity space. So it turns out that that's what I would call the valence regime. So that is where you can best study the partons in the nucleon, the quarks in the nucleon that have that make up the quantum numbers of the nucleon, right? And so and they happen to have the highest momentum in the nucleon typically. So that's the Bjorken X variable, for those of you familiar with that. So that high X valence regime, that's going to be JLab territory always, I think, for two reasons. One is the cross sections are tiny, so you need high luminosity. And the other thing is that kinematically, it is naturally where we sit. It's actually what the lab was tuned to do, and there's still lots of mystery there. The other thing I can say is that for other kinds of studies, like actually we work together on and things where you want to look at say the partonic structure, and what you really need is this whole big picture, right? You need not just the valence regime and low energy, you need to see how that links to the high energy regime and vice versa. You need to be able to go back because you're really looking at how things change across scale. You need both and maybe something in the middle like compass or something like that, right? You need information from multiple experiments at multiple kinematics. And so that will be another role Jefferson Lab will always have.
And you will learn more about small x starting from not far from now. Last question.
Yeah, is there an agreed upon distinction between what falls under nuclear physics and what falls under particle physics?
That's an interesting question. It's a funding decision. So what kind of neutrinos are particle physics neutrinos? Neutrinos that come from an accelerator, right? If these are neutrinos from the sky that might be hundreds of GeV higher energy, they are nuclear neutrinos. So it's actually historical, and funding is the real answer, although it's funny. It's because what funding agency, like this is a nuclear physics funded laboratory, because a lot of what we're doing are these questions that involve nuclear physics. Obviously, a lot of what we're doing also involves particle physics, and particle physics now, physicists are talking a lot about quantum chromodynamics and looking at nucleon structure. So from a science community, maybe not so different in part. But there is also this other distinction, but it's sort of historically what was funded when, right? What this used to be super high energy physics, like way back 20 years ago, right? This is what particle physicists were doing, right? Now we move along. But it's also, I think, whether you're studying QCD, although particle physicists do some of that, but that's really nuclear physics regime. And then the other thing is if you're creating new particles. So if you're really trying to study standard model kinds of pictures and the full panoply of mass and new particles, that's more particle physics. I would say, generally speaking, we're trying to understand the structure of ordinary matter.
But then it turns out that LHCb is producing tons of new particles, new hadrons, and new whatnots. And so they're doing nuclear physics at this point that everything is mixed up.
Yeah. So scientifically, there's not so much of a difference, but.
Okay. Good. I'm happy that you're asking so many questions. We will be running a little bit late in the schedule, but that's what we're here for, to discuss and more stuff. Next thing, we will go out, well, we can grab something to drink or so, but we go out also for a good picture. And after that, from our timetable, we should then come back at 3:45. I think it was written there for Matt's for Matt's lecture. We may allow ourselves 5 minutes or so time to come back and to go out and take a couple of pictures. Also, we don't have a professional photographer, so we may have a few hiccups along the way. But anyway, so 3:45-ish, we can come back and proceed and go from high to small x.
As well. That's true. That's true.
Okay, can people on, I'm hearing myself twice, on live stream confirm that they can hear now?
Testing. You guys hear me online? Sounds like yes.
Okay, yeah, okay, yeah,
Yeah.
you're good.
Okay.
Great.
Okay, so I let you, the student, Matt Sievert from New Mexico State University, and he will talk about intro to custody and give us an intro to custody and small
Very
okay.
good. All right, thank you guys very much. It's a real pleasure to be here. Glad I was able to take Alberto up on his invitation at last. So I'm not 100% sure how straightforwardly it's going to go, but I wanted to try and give a Blackboard talk for the lectures that I'm giving here at the school. My personal philosophy is I would rather cover something in more depth to make sure you guys are actually getting it, even if it means that I have to sacrifice some of the scope that I would like to try to cover. So I'm going to try and make this work on the whiteboard here. I wanted to point out some resources for you guys. So if you go on Indico, just in case you're not already familiar, if you go to, let me share screen. There we go, got it, thanks. Okay, so just so that everybody's on the same page, if you go to the Indico page, you can go to the detailed view if you're not already there. If you scroll down to the lectures, you'll see the lecture material. I've uploaded 2 files here. One of them is the PDF version of the lecture notes that I'm going to be going through on the board. Don't worry about following through all the stuff there, but if you miss something that I go through on the board, you can look it up in more detail there. I've got some figures that I'm going to be showing here on the screen. That's the figures file itself. So for the most part, this is the kind of thing that I'll keep on the projector, and then I'll just work on derivations and stuff on the whiteboard and then jump back and forth to make comments. So, okay, without further ado, I was asked to give the introduction to QCD and the introduction to small x physics, which are of course different things, but they fit together very naturally. So I'm happy to have the opportunity to sort of tell the story from the very beginning. I'm not 100% sure how well the timing is going to work, so we'll see whether what I think is one lecture actually turns out to be one lecture, or if we have to renormalize the charge a little bit. So, okay, without further ado, let's dive on in. When I first sat down to formulate what I wanted to say to you guys, the natural question that I wanted to begin with, of course, is what is QCD? Of course, QCD is quantum chromodynamics. There's a very simple, precise way of stating exactly what QCD is. QCD is the non-abelian gauge theory of SU3. And as I started trying to unpack that, I realized it was going to take me a whole lecture in and of itself just to explain what does that mean before we actually start getting into the nuts and bolts of Feynman rules and things that make QCD unique. So I think answering this question, what does this mean, is my goal for today. So I wanted to start by sort of localizing us in the scope of theories, quantum field theories that we use to describe fundamental interactions in nature. Am I still screen sharing or not? Okay. So just to orient ourselves, the language that we use to describe fundamental interactions of particles are relativistic quantum field theories. That is our best and or only way to marry together the Heisenberg uncertainty principle of quantum mechanics with the Einstein relation that allows you to create mass from energy and vice versa. Quantum field theories are fundamentally a multi-particle description of nature, and that's inevitable. It's necessary when you can have fluctuations in the energy that then can go into creating masses. So particle-antiparticle creation is a fundamental aspect of quantum mechanics plus relativity, and that's the part that quantum field theories solve elegantly. Of quantum field theories, the trivial ones we call free theories, but they play a really essential role in the formulation of the interacting field theories. That's because the free theories effectively define what are our particles. So what do I mean by a free theory? Let me start there. Okay, so of our quantum field theories, The non-interacting or free theories, these are theories whose defining property is that their equation of motion is linear. And that's because these give you a linear superposition of independent solutions. Linear superposition principle. Oh, and by the way, please interrupt me at any point if I say something that's unclear, if I say something that's blatantly wrong, if you can't read my handwriting, I thrive off the dialogue. So please feel free to ask questions. That also goes for people online. So for example, the familiar Klein-Gordon equation. The Klein-Gordon equation comes from the Lagrangian for a free scalar field. 1/2 d mu phi plus 1/2 m squared phi squared. And this gives you the equation of motion, which is d mu plus m squared phi is equal to 0. Why is this particularly interesting or special? This is a linear equation. So if I have two particles that are both solutions of the Klein-Gordon equation, they don't interact with each other. The solution containing two particles is identical to the solution of one particle plus the solution of the other particle. That's the definition of what we mean by a non-interacting theory. So the criteria for what are my particles are, what are all possible field theory Lagrangians I can write down? Do I need to jump back and forth? Everything okay?
We stop it sharing.
Yes, okay. So the free theories define what are our particles. So we classify the Lagrangians based on what Lagrangians lead to linear equations of motion. Those are simple. Those are Lagrangians that are quadratic at most in the unknowns, which are the fields themselves. And so you can just start enumerating what are all possible Lagrangians that you can write down. Free scalar theory, free spinor theory, free vector theory. You can go on down the list. And this defines the particles based on essentially any possible representation of special relativity. The transformations of special relativity are encoded in the symmetry group called the Lorentz group, and all possible solutions for that algebra describe all possible free particles. So that's sort of the boring part, but it's quite non-trivial to construct what are the allowed particles in nature. When I teach this in class, I tell my students, we have constrained God by writing this down. We have found out what are all possible structures that are consistent with special relativity and nothing else. So this is a complete basis with which to view the more interesting theories. The interacting theories, of course, include the ones we start off with, phi cube theory, phi fourth theory. Yukawa theory is a nice example, the effective theory of protons and neutrons interacting by pion exchange. There's quite a lot of non-trivial physics you can do in the interacting theories, but there's a very special, unique role played by gauge theories. And this is the part that I really want to unpack for you guys in detail today. What makes a gauge theory work? Why is it special? And the shining example that we have of a gauge theory is quantum electrodynamics. QED is the gauge theory of U1 gauge symmetry. And I want to unpack what that means for you guys, because this is our template then to try and understand what is different about QCD. There's essentially one change that changes the abelian gauge group U1 of QED into the non-abelian 3x3 matrix group of QCD. And that one tiny change in structures that are otherwise very similar changes everything about the physics of the theory. So this is where I wanted to start. Okay, so before I dive into QED itself, I want to talk a little bit about how we are going to use it, because most of the things that I have to say are based on perturbation theory, which is a good old tried and true method that works wonderfully for most quantum mechanical systems, but it fails in some really essential ways when it comes to QCD. So there are some things that we will get right within perturbation theory, and there are some things that we will get very, very wrong. So before we start going down that rabbit hole, I want to be clear on the scope of what we can do. So a few comments about perturbation theory. That's okay to figure out when to go back and forth. So of course, we know the nice solutions for the linear theories. In general, you don't know the solutions for the complicated nonlinear theories, except in very special cases. So we need systematic approximation strategies which allow you to approximate the solutions. And that's where perturbation theory really shines. Perturbation theory is a systematic approximation. And that systematic approximation means something important. It means that the error is controlled. So the shining example of this is you calculate some cross-section in QED. And this thing is a function of the coupling constant. If you could, alpha E, I'm sorry. If you could solve everything about QED directly, because you're just that smart, your answer would be a function of this coupling constant. The idea is that we don't have enough information to reconstruct the exact solution, but under the assumption that the coupling constant is much less than 1, you can expand this in a Taylor series. So you get the cross-section evaluated at, let's say, alpha equals 0. That's the 0th order piece. And then you would have something alpha ENM to the first power times the cross-section, which is the first order cross-section, and so on. This is all very simple textbook stuff, but the thing that underlies all of this is a very critical assumption. At the end of the day, what you're doing is essentially just a Taylor series expansion in your physical observables. That doesn't always work, and we run into exactly these instances where this Taylor series approximation fails. So this assumes a smooth expansion as a function of alpha EN, or whatever your particular coupling constant is. And I wanted to point out a particular example where this is known to fail quite dramatically. The example that I want to point out has very little to do with nuclear physics. It's the BCS theory of superconductivity. So this can fail dramatically. So BCS theory of superconductivity describes what happens when a normal metal undergoes the superconducting phase transition. And when you undergo that transition, there's a radical change in the degrees of freedom in the system. The normal metal is described by electrons that are moving through approximately free bands. But the superconducting state is described by Cooper pairs. So the reason that I wanted to pick on BCS superconductivity is that it illustrates very clearly that you can have a phase transition that describes a radical realignment of your degrees of freedom that cannot be captured in perturbation theory. Radical realignment of degrees of freedom, by which I mean the electrons or effective electrons. These are electrons with an effective mass and an effective charge because they're not in vacuum, they're in a material. But these degrees of freedom get totally replaced by Cooper pairs. I think I've got enough space in the corner here. I don't want to go into a great detail about the BCS theory, but the example that I wanted to show you is the result from the binding energy. So this is the result for the BCS mass gap equation. It's equivalent to specifying the binding energy of a Cooper pair. It is 2 times the divide frequency times the exponential e to the minus 2 divided by V naught times rho of EF, the density of states at the Fermi surface. Most of the structure here is not terribly important for what I want to tell you. The one thing that is particularly important for what I want to tell you is the functional dependence of this result on the strength of the interaction V naught. V naught is like the coupling constant. This is like alpha S. It tells you how strong the interaction is between 2 electrons that may or may not cause them to form a Cooper pair. If this is my exact solution, which some smart person could come up with, if I were doing perturbation theory, I would want to do a series expansion of this and try to construct it order by order in V naught. And as soon as you start trying to do that, you realize that there is a very big problem here. This function is of the form f of z equals e to the minus 1 over z. That kind of behavior in the exponent is referred to as an essential singularity in mathematics. And that essential singularity breaks the series expansion in unrecoverable ways. So this is just a plot of that function. Here, I just take it and plot it along the real axis. Let me share screen.
It's shared.
Oh, it's still sharing,
No, no,
okay.
You just teach.
Okay, thank you. So the potential here is shown going from positive to negative values. Here on this side, it looks nice and smooth, not too much of a problem. If the coupling goes to 0, then the binding energy goes to 0 and everybody's happy. But if you look just slightly from the other side, if the potential is just slightly negative, then this thing explodes in a crazy way. This shows that the approach to that singular point is sick. You get different answers depending on whether you come from the right or whether you come from the left. And the problem is even worse than that. If you regard this as an analytic type function in the complex plane, or I regard V0 as something that could be real or imaginary, I get a different answer for every direction you could possibly approach the point with. So the point is that this effect is a non-perturbative effect. Why do I say non-perturbative? Because if you try, you cannot find it. So suppose I take this expression and I try to do a series expansion in it. I would say E binding is approximately, then I would take the first term of the Taylor series. I would try to replace V with 0. And then I would get e to the minus infinity, which is 0.
Professor, would you mind waiting one minute while they're
Sure.
logging back into Zoom?
Oh, no problem.
Sorry,
It's not being displayed right now.
Just let me know when to go.
Sure, sorry about that.
Yeah, sure, go ahead. I'll repeat the question once we're reconnected.
Thank you so much.
Sure.
So you said that we can do the perturbative expansion when the coupling constant which is alpha is much less than unity.
Yes.
So in this regime, is it much greater than unity?
No, not even necessarily. So even if this coupling is small, even if in this example V0 is going to 0, that still doesn't work. There is no value of V0 small enough that will make this work. The function itself is fundamentally sick. Exactly. And that means that this kind of physics will never be capturable within perturbation theory. Are we back? Also. Okay, so the question was, why does it fail? Does it fail if V0 is not small enough? Because usually perturbation theory works when your coupling is small. No, this is an even worse problem than that. This is a problem that no small enough V0 will ever solve. So if I try to expand this thing, the first order term in the Taylor series is 0, or the 0th order term is 0. Plus, now if I try to take a derivative, you'd say, okay, fine, I've got my coupling is V0. I should take a derivative of the binding energy with respect to V0, evaluated V0 equals 0. Well, I take the derivative, I'm going to get some polynomial in front, but I'm still going to get that e to the minus infinity afterwards when I plug in V0 equals 0. So even the linear term in the Taylor series, this is still 0. And if I go to the next term in the Taylor series, this is also 0. And so you see what happens. If you try to take something of this form and reconstruct it perturbatively, you can't. You simply get 0 to every order in perturbation. And I would turn this thing around and throw it back as a word to the wise. Often you will see theorems that are proved and written with capital letters in the field. And they say, I have proved to all orders in perturbation theory that this is true. Does that mean it's always true? No. Non-perturbative effects can never be expanded in a series like this. So a proof to all orders in perturbation theory is not the same thing as a proof to all accuracy in your exact theory. So the point is that perturbation theory is great. I'm a big fan of perturbation theory, but we should be aware of its limitations. There are some fundamental non-perturbative effects that generally come in this form. There's a reason that this essential singularity shows up. It shows up in the PCS theory for the superconducting phase transition. It shows up in QCD for the confinement phase transition, when you generate those 1000 MeV worth of mass for the proton out of 10 MeV worth of light quarks. So non-perturbative effects often have this form, and you can see very clearly why that fails. Now, this is only one of the ways that perturbation theory can fail. Even when perturbation theory is working, it may not work the way that you expect. So let me show you a particular example of something that you would try to calculate perturbatively, and it would start to work, but then stop working. Okay. There we go. Still sharing. All right. So the second skeleton in the closet that we don't like to talk about that much is the fact that perturbation theory usually doesn't converge unless you're incredibly lucky. The perturbation series usually does not converge. And that's a problem. Normally, we like to pretend that these kind of things are convergent series, just like a geometric series where you say, I calculate to NLO, and if that's not good enough, then I'll roll up the sleeves and calculate to NNLO, and if that's not good enough, then I'll hire a postdoc who will calculate to NNNLO, and so on and so forth. But that's not always going to help you, and that's something to keep in mind. So this is a simple example. Here's a toy integral, an integral that you can do numerically without too much challenge. It's an integral from minus to plus infinity of an exponential. You have a nice Gaussian convergence factor, and then just something else to make it more interesting, a quartic term up in the exponent. This is something very nice where I can do a series expansion of the integrand if I want. Then I get a polynomial times a Gaussian, and then I can do the Gaussian integrals. So this is exactly a comparison between the exact numerical solution shown in black and various perturbative approximations to it shown in the different colors. And what you see is that, let's say I start at n equals 2, so I guess that would be NLO. That's this dark red curve. And you see it does a relatively good job. It doesn't capture it very well when the coupling starts to get large, but you don't expect it to. And when the coupling is small, it fits beautifully. So then you roll up the sleeves and say, okay, let me go to NNLO, n equals 3. And now you get this blue curve. And if you closely compare it, it is a little bit closer to the true answer. So if the coupling is small, yeah, it actually is getting better, although you probably had to work 10 times as hard for about a 1% improvement in accuracy. But the problem only gets worse from there. You see that as you go to higher and higher orders, 4, 5, even 10, the convergence slows down and even reverses. So as you go from second order, third order, fourth order, fifth order, 10th order, the convergence completely breaks. And in fact, even if you could calculate a 10th order calculation, which don't try it, it's a trap, it wouldn't help you because the perturbation series itself is not convergent. So keep these things in mind as we try to do calculations in perturbation theory. It's a systematic way of organizing our approach to the quantum field theory, but it has severe limitations that we should never forget. Questions so far? By the way, this is referred to as an asymptotic series. Yes.
Is it pretty general for the three convergence is worse if you go to higher order, or is that just a example?
I don't know enough to tell you like on a theorem basis whether it's guaranteed to happen like this. My understanding is that for most physical theories, they are asymptotic series and they don't converge, and only for specially engineered situations do you actually have a nicely convergent series with a finite means of convergence. Yes.
This feature for the high order term only confirms the fact we use Taylor series. We can use other expansion series like Cherenkov series or stuff like that.
So the question was, if you did a different series expansion, maybe not a Taylor series, but something else, would you get better convergence? That's an interesting question. I don't know the answer. It would be interesting to try.
The Taylor series are known for being bad at some special cases.
Yeah.
Where the Cherenkov polynomial work really well.
Yeah, it's interesting. I wouldn't be surprised if certain choices of the basis for the expansion work better than others, but I would be surprised if changing from a strict Taylor series to some other kind of series could change something from being asymptotic to being convergent. So you might get a greater, let's say, regime of convergence before it starts to go bad. But I would expect, just personally speculating, that changing from a Taylor series to something else would not fundamentally solve the problem. Yes.
Another thing, can it be that you expand not around lambda equals 0 or v naught equals 0,
Yep.
then you expand a little bit away and the thing changes? Can the
Yes.
choice be a problem?
Yes, actually, and that sets me up beautifully for what we're going to talk about by the end of the week. Some famous people in the field like to say that the small x physics, or the effective theory of small x physics, called the color glass condensate. Let me write this down. You'll see the abbreviation CGC. It stands for colored glass condensate. This is the effective theory of QCD at high energies and high densities. High, let me say, Mandelstam S for the energies and high rho for densities. Both of these things happen when you have low X, that is X Bjorken goes to 0. And we'll talk more about what this means in the next several lectures. So normally when we're doing perturbation theory, we do it as an alpha S expansion, starting with the free theory, starting with the vacuum. And we do perturbative corrections relative to the vacuum. The CGC effective theory is a different perturbative expansion, starting about a different initial condition. This one starts about the classical solutions or the classical equations of motion, which are called the Yang-Mills equations. And one does a perturbative expansion in those. But that's still perturbation theory. So when you hear things said in the literature, sometimes you hear people say that the CGC describes non-perturbative physics. I wouldn't necessarily agree with that. You're doing perturbation theory. It's still the same assumption about a smooth ability to expand your solution as a Taylor series, but you're starting about a different condition. It may be not simply related to the vacuum. In fact, it's related by a resummation of higher order corrections from the vacuum, which is the next thing I want to talk about. But I think it's still perturbation theory. Yes, sir.
So you're using the perturbation series to find out something which you do not know, right? You don't know the exact solution.
Right.
In this example, you know the exact solution, hence you know how far you're actually straying off the path.
That's right.
In the actual scenario, when we do not know what the exact solution is, how do you know we are straying off?
Very good. The only way to do that is to compare what happens to your solution as you compute higher orders. So if you computed n equals 2 and you only knew the red curve, and then you went back the next year and you computed n equals 3, you would say my solution is getting better. Well,
Why?
I guess maybe you have to calculate a few. Let's say I knew n equals 1, 2, and 3. You want to compare the difference as you go one order higher. If I go from n equals 1 to n equals 2 and I see some difference, and then I go from 2 to 3 and I see a smaller difference, that's an indication the series is converging. Again, that's another thing to always keep in mind when you see comparisons of theory with data, when they say LO prediction, NLO prediction, NNLO prediction. If the distance between those curves isn't getting smaller, your series isn't converging. So that's a good point, that you don't know what the solution is. The only thing you know is how are higher orders related to each other. And when you start seeing the higher orders not get smaller anymore, that's when you should start to really be worried that you're wasting your time. Okay, so this was asymptotic series. I've talked about some of the ways that perturbation theory can fail. Yes, ma'am.
I'm a little confused because I thought that earlier you said the higher order you get, the worse your convergence gets. But
Yes.
you said that as you go to higher orders, you should be seeing smaller differences.
Yeah, so what I mean is, as you increase n, you see different behavior if n is small and you go up versus if n is large and you go up. So I'm talking about going n equals 1 to 2 to 3, where hopefully you're still in that semi-convergent region, and not n equals 10, 15, 20, where you're in the badly divergent region. Does that make sense? Okay.
But also, I guess for like lambda equals up to 0.2,
Mhm.
n equals 10 would be a better approximation to the exact solution than n equals 3 or 4. Is that right?
I don't know. I would have to really zoom in on what's going on here. It's not immediately obvious to me that n equals 10 is a better description down here. Maybe it's not. The other thing to notice is that the failure of the convergence happens earlier and earlier in the coupling. So maybe at n equals 4, lambda 0.6 or lambda 0.5 was good enough for your perturbation theory. Now if you try to push it to 10, the thing is breaking by 0.2. So small coupling gets harder and harder to achieve the higher you go, which is again perversely backwards from what one would like in a convergent series. Okay, so I've talked about some of the ways that perturbation theory can fail. Let me talk about one of the most crucial ways that perturbation theory can succeed. Perturbation theory is sort of anchored to what degrees of freedom are you doing your expansion in. If I'm starting off with electrons, it's not going to be able to find the fact that my degrees of freedom might have changed to Cooper pairs. But it can describe the fact that my electrons might be changing as a function of scale, as a function of energy, as a function of density. It can describe a slow evolution in the degrees of freedom, but not a radical subform. So this slow evolution of degrees of freedom goes by the name of resummation. And there are a couple of really critical examples that show up in QCD all the time. Both of them come from essentially the same ingredient. Suppose you have a single particle, let's call it a quark, and then it splits, and then it radiates the soft fluor. We'll talk more about what this means. So let me just, for the sake of concreteness, let me say this particle has energy E and momentum 0, spatial momentum 0, maybe in the transverse direction. Say the gluon splits off and it carries some fraction Z of the energy. Z is just a dimensionless number between 0 and 1. And it has some transverse momentum K. Then the quark which recoils against it just has, by momentum conservation, 1 minus ZE negative K. This is essentially the standard building block for pretty much all of your higher order corrections. Most everything in QCD can be boiled down to something built out of these light front wave functions themselves. So what can happen in your series expansion is that a process like this is down by a factor of the coupling constant. Let me talk in QCD terms. So you might have weak coupling, alpha much less than 1. That means the probability that this quark actually branches is very small, and the probability that it undergoes 2 branchings is so small you can ignore it. But what you can have is an interesting competition. Suppose that I have this and now I integrate over these unobserved particles. I integrate over the phase space. Depending on exactly what observable you're looking at, you can get some particularly interesting integrals. You might get something which is small by a factor of alpha s, but then you integrate it, let's say, over the transverse momentum. That transverse momentum integral looks like this. You get a dk perp squared. It's a 2-dimensional integral over the transverse momentum. I get rid of the angles. Usually the angular integral is not terribly interesting. And this denominator 1 over k perp squared is part of the result that you get when you calculate what that wave function looks like. This integral is very interesting because the form of this integral is integral dx over x, which, as any student of calculus will tell you, is going to give you a logarithm. This logarithm is then very sensitive to what those limits of the phase space are. So if the maximum transverse momentum is the energy coming in, I guess here I'm doing it in squares, the minimum transverse momentum is some cutoff. I'm just going to make up a name for it. Let's call it lambda. This integral being logarithmic gives me not only alpha s, but an associated logarithm of the energy compared to that cutoff scale. So this is an interesting competition. Alpha is small, but you may have a phase space which is large. If the energy E is really, really huge, and that cutoff lambda is really, really small. So pretend this is, let's say, square root s at the LHC. And pretend that this is, oh, I don't know, lambda QC 1G or so. If there's a massive difference in orders of magnitude between these scales, then the logarithm between those two scales could actually be large. It could be so large that it starts to compete with the smallness of alpha s and screws up your perturbation series. So you could have alpha s much less than 1, meaning your weak coupling is still valid, but a large logarithm, meaning e squared much greater than lambda squared, not just bigger, but so big that it's exponentially bigger. The logarithm itself is much larger than 1. That means e is not just a factor of a few larger than lambda, it's exponentially larger than lambda. But if you open up so much phase space that that large logarithm now starts to compete with the smallness of your coupling constant in a very systematic way. So on the face of it, this looks incredibly dangerous. You say, well, I had weak coupling, I had perturbation theory, but now I just killed it. But this large logarithm only comes from very specific places. It only comes from specific phase space integrals that have to integrate over a very large range. So this actually is a success story because you can identify what process generates that logarithm. And even in the case when alpha is small, but the log is large, such that alpha times the log is not much less than 1, right? In strict perturbation theory, I would say, who cares about the log? That's an alpha s correction, that should be small. But if the log is large enough, then this number can be order 1 and not small at all. This is still much larger than alpha s. Alpha s is still small, but alpha s times the log is large. When you have this situation, this is not small, you can't neglect it. that means that one factor coming from this kind of branching is of the same order as two of them. And that's of the same order as three of them. And that's the same order as all n of them for any n from 0 to infinity. So you see, this is how the perturbation theory is breaking. It's breaking because each higher order correction, which is always associated with this log, is not small compared to the one that came before it. But if you can identify the source of those logarithms, then you can resum them. Typically, the strategy is, let me figure out the process that created this and write it like a differential equation. If I can write it as a differential equation, something like derivative with respect to log e squared over lambda squared. That derivative will tell me the coefficient in front. You can write it as a differential equation, and if you're smart enough to solve that differential equation, that solution is the exact solution of the logarithmic problem here. This is referred to as a leading logarithmic resummation. Leading log resummation. So we'll talk more about this later. There are two extremely important examples of how this shows up, both of which come from this fundamental quantum branching. The one that I'm illustrating here is a large logarithm coming from the transverse splitting. This is essentially saying these guys recoiled so hard that they're back to back. These guys have so much relative momentum that I can ignore anything that came before it. That transverse momentum ordering of this type is what is responsible for D-lap evolution of PDFs. And we'll talk more about what that means. The other type of logarithm that gets resummed in the same way is the logarithm of this longitudinal variable c. If you do the same exercise here, you can get another logarithmic integral, which looks like alpha s integral dz over z. Again, the form of that wave function comes with a 1 over z. That z being specific to the gluon. So in the limit, when z is very small, that means that this gluon carries a very tiny fraction of the original incoming energy. This integral could be as large as 1. This gluon could carry 100% of the energy. But if this thing starts going down to 0, it's going to blow up. So you have to cut this thing off at some minimum scale, something like lambda squared divided by the energy squared. This cut comes from the kinematics, it comes from the process. We'll discuss this more. But this kind of logarithm coming from the longitudinal integral is again alpha s log e squared over lambda squared. So this is the same kind of situation. Different logs, they come from different physics. This one is responsible for what's known as BFKL evolution. You'll also see words like BK or Jimwalk or God knows what else. There's a huge number of acronyms associated with this. But these things are coming from the evolution of the branching. And the fact that you can have many of these is telling you that this process, these evolution equations which describe that, can describe a whole sequence of nested cascades of this order, as long as each one is kinematically ordered with respect to the previous ones. So when you do this, you can use perturbation theory to push the limits of perturbation theory. Resummation is a way of starting with one set of degrees of freedom, like expansion around the vacuum, and then performing this sum to effectively get a new summation, which starts with the classical equations of motion. That's sort of where I'm going for later this week, to talk about BFKL evolution and how that leads you to the high density regime and how that leads you to semi-classical regime. Okay, this is a good point to pause. How am I doing on time, and are there other questions so far?
You're still 15 minutes, a little bit more 20.
Okay, we'll see how much I can cover in 20 minutes. Okay, this is going to take a bit to get to. Yes, ma'am.
So my understanding is that you can still use perturbation theory here. You just kind of have to rewrite your expressions in a way that you don't have all of your units the same order.
Yes, that's right.
Can you explain again how the kind of the branched pattern diagram plays into that?
Oh, sure. Basically, so this picture, let me talk about D-lap. D-lap was the one where I had some momentum here, but this splitting is huge compared to that one. Suppose I start off with some K perp K1 here initially, where these are all transverse momentum. Then I've got some branching here. this is K2. If my K2 is much, much larger than my K1 might as well have been 0. And then I'm exactly back to this situation. And I get this large logarithm from the back-to-back splitting. Now, if this one undergoes another splitting, K3, which is much larger than K2, then that also satisfies the same condition. This K2 is large compared to K1, but you can forget about it compared to K3. This one, when you integrate, you're going to get another alpha and another log. And as long as each splitting is much, much larger than the one that came before it, you will always get not only the alpha, but also the log. So that's the conclusion that this strongly ordered cascade, this has to satisfy K1 much less than K2, much less than K3, much less than on down the line. As long as you satisfy that strong ordering constraint, you guarantee that every time you integrate over another branching, you will pick up another log. So that's strong, the set of terms that are unsuppressed are exactly these terms, the ones that are always counterbalanced by a small coupling but a large phase. So it's possible to deal with this because only from this very systematic structured process do you get that breaking. And so if you identify where and how it happens, you can basically get the exact solution to that part of it and staple it together with a weak coupling expansion for the non-logarithmic part. Does that make sense? Okay. Yes.
So does that mean then you have to check that other orderings don't give you more logs?
Yes, absolutely. So it's absolutely critical to make sure that you have found the largest set of logarithms. For instance, if I'm working on all of this for polarized evolution, I might start calculating single logarithmic corrections of this type and then discover accidentally that there are double logarithmic contributions that show up where you have both of these effects at the same time. Those double logarithmic contributions are much more important than this. This would be down by 1 alpha. Those contributions would have 2 logs for every single factor of alpha. So you can even also take that a step further and say, well, what about NLO corrections to this? I could have alpha squared corrections. You could have this with just a simple quantum correction on top of it. And then you can do the whole schmear all over again, but now these things would have 2 powers of alpha. So there's a balancing act. There's a competition between how many powers of alpha do you have, how many logs do you get, and what is your resummation parameter. The thing that defines this uniquely is the statement that alpha s log e squared over lambda squared is of order 1. That's what defines the leading log resummation. But yes, one can improve and go beyond that. Okay. So in my remaining 10 or 15 minutes, I'd like to say a few words about gauge theories. Okay. So all of our gauge theories are predicated upon the best example that we have, which is QED. QED is the abelian gauge theory of U1. U1 symmetry. I would like to unpack those words to whatever extent I can in the time that we have and relate them to the Lagrangian that everyone has seen and worked with. Psi bar I d slash minus m psi minus 1/4 f mu nu minus e psi bar gamma mu psi a mu. I'm working under the assumption that pretty much everybody here has at least a passing familiarity with this. So if that's not the case, please let me know and I can do some more explaining. So the QED Lagrangian, this is LQED, consists of 3 pieces. This is, of course, the free Dirac Lagrangian. This is the free photon Lagrangian. And this is the whole thing that we work so hard to get. This is the interaction term. So QED is a theory of fermions described by the spinor field psi and vector bosons A, which are referred to as the photons. And those vector bosons cause the entire source of difficulty with the gauge. So psi is fine. That's good. You can construct all kinds of nice theories like Yukawa theory. But A mu is the tricky one. And the reason that AMU is tricky is because a vector in 4 dimensions has too many polarizations. You have a problem with the polarization states of the vector field. You also have polarizations for the spinors, but that's not a problem. You can have spin up, you can have spin down. The problem is that in 4 dimensions, you could have up to 4 different independent polarization vectors for the gauge field, the photon field. And one of those polarizations is deeply sick. You have no hope of ever quantizing. That problematic polarization is what I'll refer to as the scalar polarization. That's the one if AMU is proportional just to a perfect gradient. This is a perfectly allowed polarization in 4-dimensional spacetime. You could construct a field that satisfies this. The problem with this is that if you try to quantize it, it leads to negative norm states. This is just, it's a sick mode. It cannot be quantized. It has no place in quantum field theory. This is also sometimes referred to as the time-like polarization. Negative norm states. So the problem with this is if you try to do it and then you calculate what is the absolute value of my photon field, you can get a negative number from this. And that's just not compatible with any quantum theory that you can come up with. So any theory that you have that has any vector boson has to get rid of that scalar polarization somehow. If you have a massive vector boson, then you can just forbid it by constraint. That's referred to as the Proctor theory. But if you have a massless vector, you can't get rid of it the same way. You have to get rid of it in a very different way. And that's exactly what QED accomplishes. The way that QED gets rid of these unphysical scalar polarizations is through gauge symmetry. It becomes a symmetry of the Lagrangian itself. And the symmetry that allows you to define the photon in a meaningful way is built by extending the symmetry that was already there in the 3 Dirac Lagrangian. So if I just start with the 3 Dirac Lagrangian, just non-interacting fermions, psi bar I d slash minus m psi. It already has a nice symmetry that can become the basis for adding a photon later. This symmetry is a global U1 phase rotation. What do I mean by this? I mean specifically the transformation psi prime of x equals e to the I phi psi of x, where phi is a constant. Why is this U1? U1 means the group of, let me call it 1 by 1 unitary matrices. And if you think about it for a second, you realize a 1 by 1 matrix is just a number, and a 1 by 1 unitary number is just a complex phase, just e to the I phi. So there is no actual matrix structure here. Not a matrix. And that's very important. This is why the theory is abelian. Abelian is an algebra term. It's named after the mathematician Abel. It just means commutative. And the fact that this is just a number, just a scalar that has no matrix structure to it means obviously it's commutative. Scalar multiplication is commutative. That's the part that's going to change when we go to QCD. If I have a matrix that enters here, those matrices do not commute with each other. And that's the source of what's going to fundamentally change the structure for QCD. So this transformation, what does it do? It basically rotates the real and imaginary parts of your field. I could expand it out. It's in the notes. Let me maybe sketch a picture instead. If I write out psi of x in terms of its real and imaginary parts, then this is effectively changing the axes of those real and imaginary parts. So I can have the real part of psi, the imaginary part of psi. If my field is here, if I have psi, which has some value for the real part, some value for the imaginary part, then psi bar is the reflection about the imaginary axis. Psi bar would be down here. This is the complex conjugate. So keep in mind, of course, that psi is the annihilation operator for a particle. This describes electrons. Psi bar is the annihilation operator for a positron. This describes antiparticles. So having these axes that says a point up here is the particle, its mirror down here is the antiparticle is a way of defining what my degrees of freedom are. Now if I go and I rotate those axes, now I have, let's say, real part of psi here, imaginary part of psi here, then now this same psi is going to be reflected differently. It's going to reflect across the new imaginary axis. And your psi bar would be over here. So this transformation looks pretty innocuous, but it's doing something pretty substantive. You're redefining what is the particle and what is the antiparticle. And your Lagrangian doesn't care. It just knows I have some particles and I have some antiparticles, and I know how many more particles than antiparticles I have. But it doesn't care which one is which, and it doesn't care exactly how you define it. So the meaning, I would say, if I try to ascribe some physical interpretation of this, the meaning is that you are smoothly rotating particles into antiparticles. You are redefining what's the particle and what's the antiparticle. And because the Lagrangian is invariant under this symmetry, right? Hopefully this is obvious. The Lagrangian is invariant because if I do this, then I just multiply psi by e to the I phi. I multiply psi bar by e to the minus I phi, and these guys just happily cancel each other. So the Lagrangian is trivially invariant under this U1 phase rotation. It doesn't care what you call the particles. But what it does know is that the net number of particles minus antiparticles is a conserved quantity. So this Lagrangian is a function of the field psi, the field psi bar, and the gradient d mu of psi. It does not depend on the derivative of psi bar. So if I just expand the transformation of my Lagrangian using chain rule, the variation in the Lagrangian is however much the Lagrangian changes as a function of psi times the variation of psi, plus the variation of the Lagrangian with respect to psi bar times the variation of psi bar, plus the variation of the Lagrangian with respect to the gradient d mu psi times the variation of the gradient d mu psi. And that's it. Now I can start plugging things in, but my equations of motion are going to drastically simplify this for me. The equation of motion for this Lagrangian is, of course, the Dirac equation, which is simply IV slash minus m psi is equal to 0. So for instance, this term, if I take the derivative with respect to psi bar, that's gone. The thing that's left is 0, according to the Dirac equation. So this term is simply 0. You can also get this by the Euler-Lagrange equations in an equivalent form. Another way to rewrite this, if I reuse the Euler-Lagrange equations, I can translate the derivative with respect to psi into the derivative with respect to a gradient. So from the Euler-Lagrange equations, this is equivalent to d mu of variation of the Lagrangian with respect to the gradient, d mu psi. And the other thing that I'm going to do is I'm just going to swap the order of these two derivatives. This is a partial derivative in a particular space-time direction. This is a functional derivative that changes the function by some amount. So if I just swap the order of these two things, then this is d mu of delta psi. And now if I put these two terms next to each other, this looks an awful lot like d mu of A times B plus A times d mu of B. And that's just product rule. That is d mu of A times B. So the combination of all of these things looks like the total divergence of some quantity. So I get d mu of variation of the Lagrangian with respect to d mu psi times delta psi. This is how much my Lagrangian changes, and I already know that it doesn't change. The variation is 0. So this tells me that there is some quantity which is a non-divergent current in 4 dimensions. This object is a conserved current. It doesn't diverge, so it satisfies a continuity equation. So this is frequently written d mu j mu is equal to 0, with j mu is a conserved current. And if you actually calculate these derivatives, you get J mu is equal to psi bar gamma mu psi. And if you even expand these things out in terms of the free particle solutions, this is basically equal to the number current of particles minus antiparticles. Of course, the existence of a conserved current is guaranteed on very general grounds by Noether's theorem. So, okay, the free Dirac-Lagrangian already has a global U1 invariance because it doesn't care what you call the particle, that's up to you. The physical consequence of that is conservation of electric charge, conservation of electric current. So that even if you don't know which one's the particle and which one's the antiparticle, you do know how many more of one than the other you have. Time check? 0?
Like 5 minutes.
Okay. We'll see what we can say. Please just cut me off when I'm out of time. 'Cause I'm
Okay,
just gonna
okay, I raise my hand.
Definitely going to renormalize my lecture time. Okay. So where does the vector field come in? The vector field comes in because you've got to find some way to get rid of that scalar polarization. And a conserved current is a really clever way to do it. So suppose I have an interaction Lagrangian, just a simple piece, which is minus J mu A mu, with A mu a vector field of some kind. And this J mu is the conserved current, some conserved current. It doesn't even have to be that conserved current. The only thing that's really essential is that d mu J mu is equal to 0. If I have a Lagrangian of this type, this is extremely helpful. This is J dot A coupling, if you like, in 4 dimensions. Why is that good? Why is that helpful? Because this Lagrangian is insensitive to shifting A by a scalar mode. This solves the problem of the unphysical scalar mode of A because it reduces it to a symmetry transformation of the Lagrangian. So what do I mean? If I define A prime mu of X to be A mu of X plus a scalar polarized mode, d mu phi for some phi, then what does this do? My new Lagrangian L prime is minus J mu A prime mu, which is minus J mu A mu, that's the Lagrangian I started off with, plus the new term, minus J mu d mu phi. So this is my original Lagrangian, and this derivative doesn't talk to that current. In principle, I could reverse the order of these things using product rule. So I could write it as, let's see, minus d mu of J mu phi. I have the term where the derivative acts on phi. I don't have the term where the derivative acts on J. But since this current is conserved, that's just 0. So effectively, as far as this derivative is concerned, that's a constant, and I can just pull the derivative right past it. When I do that, this is now a total derivative. This does not affect the equations of motion at all. This is a boundary term, which leaves the equations of motion invariant. So up to a total derivative, which is irrelevant for the actual physics, this Lagrangian, an interaction of this type, is invariant under the addition of a scalar polarized mode. So this very simple vertex, this J dot A that you've seen a million times since undergrad, is a very deep and profound thing because it makes it possible to eliminate the physical role of the scalar mode. Because if I shift A by a scalar mode, it has no physical consequences for an interaction of this type. That is what makes QED special. That's what makes it a gauge theory, and that's what makes the whole thing work. So maybe this is about where I'm going to have to stop. There's a lot more that I have to say, I guess, next time about how the transformations work and sort of previewing what we're going to see with QCD. But that's the point of writing the QED Lagrangian in this form. You have the original ID slash minus M Dirac operator, you have the free photon fields, and you have the very special vertex. psi bar gamma mu psi. This is just the conserved current J mu times A mu. So the point is, the QED Lagrangian or any gauge theory uses a vertex of this type. It's always of the form J mu A mu. And this is not just convenient, it's necessary, it is mandatory. You cannot have a photon without it. If I tried to just put some other photon in there, I don't know. You put a term proportional to d mu A mu, or you put a term proportional to A mu A mu, or you put in other kinds of dependence on the vector field. Anything else that you add makes it susceptible to that stupid scalar polarization showing up and destroying your quantum theory. The only way to actually be able to do a quantum theory with these fields is with a coupling of that type. This is the minimal coupling. You can do more exotic things on top of it, but that's why this procedure goes by the name of minimal coupling. So I guess what I want to talk about next time then is what this does to the scalar polarization, how it gets rid of the scalar polarization, and how it combines together the Lorentz symmetries of space-time with the gauge symmetry of the vector field. These two things are now totally entangled with each other. This is a necessary and inevitable feature of defining the photon at all, right? You are combining space-time and the gauge dependence into a single manifold. And even though the space-time might be flat, your gauge structure could be totally crazy. So you can have curved space-time with a differential geometric interpretation, even though your space-time itself is flat. And the physics that this encodes, let me just end on the physics message. The physics that this encodes is the fact that in QED, the type of charge which generates that current, which comes from the symmetry, is a scalar kind of charge. Electric charge comes in exactly two varieties, positive and negative, but it has no direction associated with it. As a result, the equations of motion, Maxwell's equations, are linear equations. You have the beautiful superposition principle. You don't see weird things like electric fields scattering off each other. They add up just like they're supposed to. And the whole point that I'm walking through this for is to set us up for what happens when we go to QCD. In QCD, that one difference is the introduction of a direction into the gauge theory. The fact that there are now multiple independent axes of rotation, and I can perform different kinds of gauge transformations, and the theory is invariant under all of them. This transformation means that the symmetry no longer, sorry, this symmetry group means that the transformations no longer commute with each other. And that means that these vector bosons, the gluons, don't satisfy linear equations of motion anymore. That change allows gluons to interact with themselves and with each other. And that one change leads to these beams now scattering off each other, if I push the analogy. And this is responsible for all of the complexity of QCD. So, okay, I should probably stop here and pick it up in the morning. But the point is to walk through the steps of what goes into QED and then QCD. I want to really explain what is the gauge theory of SU3 and how does it radically change everything that we thought we knew about QED. All right, thank you. We had a lot of questions during the discussion, but if there's any we didn't get to, I'm happy to answer them.
Okay, so we can start. If you have questions, let's go ahead.
Sure. I think I had a quick one. When you say something like SUN is the group of all n by n unitary matrices, are we really saying SUN has a fundamental representation where it's an n by n matrix? Okay.
Yeah, so I always flub a little bit the difference between the capital SUN and the little SUN for the Lie algebra. All representations have the same Lie algebra. The defining representation, the big SUN, is the n by n unitary matrices of determinant 1.
But even with the algebra, though, like say the generators don't necessarily have to be the same dimension. Just
That's
that
right.
There's the same number of generators.
That's right.
Okay.
Yeah, so this is the defining representation of the group, and there can be higher spin representations of the same group. So in terms of QCD, that means that you've got one representation of this, which is the quarks that have a 3 by 3 set of matrices. You've got a different representation for the gluons, which are the 8 by 8 representation. And if you start stacking together multiple quarks and multiple gluons, you can make even higher dimensional representations. Okay.
Thank you.
Sure. Yes, sir.
Thank you for the talk.
Sure.
So when you were talking about the U1 EM gauge transformation, It seems to me that it's describing sort of a continuous charge symmetry.
Yes, absolutely.
Versus the typical discrete charge symmetry
Yes.
that we think about being a reflection on the real axis. So is there a discrete symmetry or set of discrete symmetries which corresponds to that SU3 structure in the same way that we have the mirroring on the real axis in U1?
I have to think about it to give you a more detailed answer. I think the answer is yes. I think that there are discrete subgroups. I think there are 2 of them that are simultaneously diagonalizable, but I would have to double check the details. Yes, I agree with your description of QED. That's how I think about it as well. Thank you. Sure. Yes.
This might be a big skill question, but I didn't quite understand what the scalar polarization is and why it's a problem.
Yeah, I didn't want to get into something incredibly technical. It comes basically from the canonical commutation relations. The fact that in order to quantize the theory, you want to enforce commutators such that your commutator of a nu with its canonical momentum pi nu should be something proportional to the metric tensor G nu. So the problem is that the metric tensor is not positive definite. The space-like parts are positive for this. The 3 space-like parts all have one sign, but the time-like part has a different sign. So if you can make this work nicely in the space-like sector, it's not going to work nicely in the time-like sector. That minus sign from the metric is essentially what gets propagated through to that normalization of the photon state and can give you something negative. So you're sort of always in this tension between, I want something Lorentz invariant, I want G nu here, but I can't put the time-like part because if I do, I break the quantum. And so you can choose either, well, maybe I sacrifice Lorentz invariance and I just quantize everything in Coulomb gauge, for instance. You can do that, but then you lose a lot of the virtues of the quantum field theory in the first place. Whereas unifying the 2 together into a single higher dimensional manifold that all transforms in an interrelated way means you don't have to sacrifice either. That you can, by making it a gauge symmetry, you can keep exact Lorentz symmetry as long as it's coupled together with the gauge structure.
So the gauge, using a gauge, like solve.
Yes, it solves the problem without requiring you to give up Lorentz invariance. Sure. Yes.
So, remember you wrote about the binding energy and its function form. Now, is that the exact solution?
I believe it is the exact solution to the BCS gap equation. That itself, as far as I recall, is a mean field approximation in Hartree-Fock theory. So it is exact in the sense that you wrote down a differential equation, that's the solution to the differential equation. It is not exact in the sense that that is everything that you could ever write down.
But if it is exactly solvable, then why you apply perturbation?
To show an example where perturbation theory is known to break. And
no, so in perturbation theory, you have unperturbed system and then you have the perturbation.
Yes.
Right? Now you know the solution to the unperturbed system. And this perturbation essentially adds on corrections to it.
Yes.
But if you start off at an EV which is already given to you, I mean, I don't know how the perturbation comes into that, if it's an exact solution.
So the idea in perturbation theory for field theory anyway is you want to always start with the free non-interacting theories. Your baseline should always be non-interacting particles that you know what they are. And the point is there are some interactions between those particles that you could never construct in perturbation theory. For instance, if you have something of the form e to the minus 1 over g, e to the minus 1 over alpha. That's exactly the form of the chiral condensate in QCD. It's exactly the form of the mass gap in BCS theory. It's a general structure. It shows up a lot of the time in non-perturbative effects. So I wanted to show an example of something where you knew the exact solution that had a non-perturbative effect in it. By the way, maybe it's worth mentioning, BCS theory cannot be solved perturbatively. You have to do Hartree-Fock to find it in the first place. If you try to calculate the mass gap using Maxwell's equations, you'll just get 0. Right? You have to do something which starts with a different set of degrees of freedom and ask for itself consistently. You cannot get it from perturbation theory starting with electrons and holes. So I wanted to start with that sort of more concrete example to illustrate when one does perturbation theory in QCD, don't think you're getting the whole story. Chiral condensate, essentially a phase transition. When you have a serious phase transition like the confinement phase transition, perturbation theory is not going to be able to go across that singularity. And that's what that singularity looks like in another case.
Okay, I would actually stop here because it's already past 5. So
Thank you.
we
We'll
have 15
continue in the
minutes.
morning.
Yeah, you can always use Slack to ask questions.
Yes, absolutely.
And then, I mean, you're here, so just I think. But I invite the students that are online just to write on Slack if they have more questions. So
Let's stay here and sequester him for another hour, right?
yeah, okay, but just to
You call me and we bring him outside to have something to eat or so.
Excellent.
Okay, just another short communication. You can subscribe for giving the seminar and the poster. The seminar only for the people that are in this room. The posters are, and the deadline is 6th of June. So please send us your title and the abstract so we can start to